Good morning. Let's wait another couple of minutes before we get started. All right, I'm going to share my screen. Okay. All right, so one thing I was trying to do yesterday was use this new spaceship operator, which I didn't before. And I had a closer look yesterday afternoon. And actually, there is a very nice usage of that. But mainly, sorry, mainly it's intended for code generation in the sense that I'm using it here, and the first thing to do is to include compare. So the compare header, you actually need that, and then you can implement the operator in your class. In this case, I chose it to be a struct just for simplicity, and it has three members, three attributes: x, y, and id. X and y are double precision numbers. ID is an integer, so nothing special happens here. And then I define the spaceship operator, so the three-way comparison. Of course, as an argument, it takes a const ref to a member of the class. And of course, it is also a const, because obviously it won't change the object which you apply it to. And I just assign a default to this. So basically, I'm telling the compiler, please go ahead and do your thing. Now, what the compiler is going to do is generate code automatically to make sure that points, so object of type point, can be compared for less than, larger than, etc., etc. And basically, this then in turn ensures that, for instance, such objects can be sorted when they are in a list, or in this case in a vector. Apart from that, I have small I have a small friend function to overload the send-to operator so that I can visualize a point easily. And basically that's it. This is the implementation of that operator, so nothing special. In the main function, I create a vector of points, and then I put some points in that. And this is something I also didn't mention yet, but something that is definitely worth knowing. So it's a vector. So basically what you would normally do is you would create a point and you would put it into that vector using pushback. But we can do something which is a little smarter, and we'll come back to that when we talk about pointers as well. But basically what you can do is you can create an object point directly into the space for the vector, where the vector stores its data. And that's done using unplaceback. So it's a little bit like a pushback in the sense that you add an element to the end of the vector, but you create it in place. And of course, that does make very little sense if your vector stores numbers or other scalars, but it can make quite a lot of sense when you store something a bit more elaborate, like arbitrary objects. So I create 5 points in total with x coordinates, y coordinates, and ID. And then I just do a sort, and as you can see, it's just the default sort method, or sort function rather, in the algorithms part of the STL. And then I just print out all the elements of point. So when I run this, you can already see it here. I get my points sorted. First component number 3. Why? Because its x coordinate is the smallest. So basically, the sort order which has been generated is that first items are sorted based on the x coordinate, next on the y coordinate, and thirdly on the ID. And that's exactly what you see here, because basically here we have 3 points that all have the same x coordinate. If they have the same y coordinate, they're sorted on ID. If they have, and then, if they have a different y coordinate, they're sorted on the y coordinate. So this is very convenient, and it saves me quite a lot of time generating code, which is basically boilerplate, because I would have to add the implementation of quite a number of operators in order to get this done, while here it's done automatically by implementing the spaceship operator. Okay, so that's pretty cool. I just wanted to show you this. Now let's turn to the slides again. And by the way, I fixed the limits here. So yeah, I had swapped these two. So in the development version of the slides, it's already there. But I don't think I merged to master. Okay. So if I have an overview, if I just have a look at the sections, then basically we are quite good. So we covered nearly everything. One thing I'll cover now is pointers. We still have to cover I/O streams, and also I promised you that we would talk about strings and regular expressions, but that's for later. Apart from that, I think we've dealt with almost everything, but in pointers I also talk about some things which are not in the slides, but which are kind of useful to know. But let's first talk about pointers. Okay. For those of you who are familiar with C, you know that pointers play a prominent role in C. And also, if you, let's say, read or talk about C++, you also come across pointers quite a lot. And although they are useful, you might wonder, well, okay, up to this point, I hardly talked about pointers. I mean, we've been talking about C++ for 12 hours. I think I mentioned pointers once explicitly in an example for dynamic binding. And I said, okay, we'll cover this later, which we'll do now in more detail. But apart from that, I didn't mention pointers that much. And the reason is that in many modern C++ programs, you actually don't need to deal directly with pointers. Sometimes you have though, and that's what we'll talk about now. But very often you can get away without using pointers. Why is that? Well, basically, if you look at a programming language like C, well, you don't have much by way of data structures. Essentially, the only thing which you have is an array, a C-style array, and an array in C and an old-style array in C++ is in fact nothing more than the address of the first element of that array. And what is a pointer? A pointer is nothing more than a variable that holds the address of some location in memory. That's what a pointer is. So if that's the only thing you've got, like in C, you're going to use it all the time. But in C++, obviously, we have a lot more data structures. We have some very nice data structures, such as vectors, such as arrays, and so on. So to just get memory space, we don't really need pointers. But we still need them for other purposes. So yes, you are, in general, you can't really avoid pointers in C++, but you would need them a lot less than C programmers, for instance, might think. So basically, if you think about data and data management, then the data you're working on is typically stored in volatile random access memory, so in the RAM of your computer. And that means as soon as either your application quits, crashes, or whatever, or you turn off your computer, that information is gone. That's pretty obvious. You're familiar with that. That's why we have hard disks, SSDs, and the like. You can see that random access memory as a sequence of bytes. And the random access memory doesn't really care what you store there. That's totally up to you as an application developer. You don't care. So at the end of the day, that means that the value of any variable is just a sequence of bytes somewhere in random access memory. And that value can either be stored contiguously, like that would happen, for instance, for floating point numbers for integers. The bytes that represent a double precision number are, of course, one after the other in memory. That's fairly obvious. Also, for instance, if you have a vector or an array in C++, you know that the elements will be stored one after another in memory. That's how these data structures work. Other variables, like for instance a list, well, it might be that list elements are scattered around memory. They do not necessarily need to be placed at specific locations. They can be anywhere in memory. But at the end of the day, it doesn't matter. It can be a contiguous or non-contiguous sequence of bytes somewhere. That's the value of a variable. That's the way we represent data in computers. So basically that means, of course, that the value of a variable, or a variable for short, has an address in RAM, because if you view RAM as a sequence of bytes, then of course you can refer to the 1532nd byte, and that is an address. So this is visualized here. I've got an integer 5 and I've got a float 3.9. Notice I'm using the F here to make sure that this is floating point value, not a double precision value, so I don't have a conversion that would be narrowing. Okay, this is my RAM, and we know that both integer and floating point, well, for float we know it's 4 bytes, for int it's usually 4 bytes. Actually, we don't really know, except by experience, because as I already said a few times, it's not in the C++ standard how many bytes an int should have. It, in my experience, always has 4. But anyway, so for instance, this sequence of 4 bytes here will store the integer value 5, and this sequence of 4 bytes will store the floating point value 3.9. And basically that means that the address of I would be the first byte where it's stored. The address of F would be the address of the first byte where that value is stored. That's basically the idea. So how do I know where something is in memory? And by the way, as a Python programmer, you don't care, because this is something that in Python you can't even do. You have no way to get the memory address of a variable in Python. So this is something that for Python people is somewhat alien. So how do I get the address of whatever in memory? Very simple. I can use the ampersand operator. Okay. Now I can assign that address to a variable, and the variable that contains an address, that's a pointer. This is exactly the definition of a pointer. And given that every variable in C++ must have a type, that means that we need a pointer type. So a pointer type is a type that holds an address to some type. So if I need to store the address of an int, then I need an int pointer, and the notation for that is int star. So int star is a type that a variable with that type can be used to hold the address of an integer. And similarly, if I need a variable that can hold the address of a float, I'd give that a variable the type float star or a float pointer. Okay, so that's fairly straightforward. Here's an example. I still have my variable I of the previous slide. I can take its address using the ampersand operator. Okay, and I use that to initialize the variable pi, and as you can see, that's indeed a pointer to an integer. So the address of I is stored in the variable pi. Similarly, the address of f is stored in the variable pf, which is a pointer to float. Very easy. So again, if I get my visualization from the previous slide again. Basically, PI points to this particular byte, which is the first one where the value of I is stored. Similarly, PF. Okay, so the semantics, PI is the address of an integer value, PF is the address of a float value. All right. What can we do with addresses? Because basically at this point, yeah, we can take the address of an element or of a variable. Yeah, so what? Well, we can use these addresses to actually modify whatever is stored in memory there. So for instance, if I write something like star pi, then I'm referring to the value of pi. And at the memory address which pi holds, indeed, there is the value 5. So these two things are sort of equivalent. Similarly for pf, star pf means the value stored in the memory location pf, and that would be 3.9. So I can use the value at that address just by applying the star operator to pi or the star operator to pf. So in this case, I'll just print the value of pi, and I'm also printing the value pi itself. This would be an address. This is the value stored at that address. So star pi is going to be an integer value, 5 in this case. Pi will be something fairly cryptic. And similar, of course, for pf. So star pf is a floating point value, so I can compute the cosine of that. And that actually better leave out the std stuff here, because it's not required anyway. But whatever. What I can also do is assign a new value to an address. For instance, if I write star pi, I can assign to that, because I'm going to change the value stored at pi, similarly for pf. So after this assignment, actually the values will change. Pi will point to a memory location where now 7 is stored. But remember that I was the name of that memory location. That was the variable. So I is now also 7. Similarly, if I change whatever is at address pf using the star operator, then, of course, no. Why is this 8.19? Apparently I changed my mind at some point. So that should be 2.1. Or I should change this to 8.19. Okay, this is weird. Anyway, so this allows me to change data which is at a given memory location. That's the star operator. So, yeah, there's a times equal. Yes. I had not noticed the star, indeed. Yeah, I'm multiplying the original value, which now I don't recall, 3.9 by 2.1, and that indeed will be 8.19. Yeah, that will teach me not to make my examples too sophisticated, because if you overlook the star, then obviously this is weird. Okay, I thought that this was very weird, because that's a really weird mistake to make. But anyway, so there is no mistake. It's just me not seeing the star operator. Okay, probably I did it just to make the point that the star operator in C++ actually plays multiple roles. So the star operator is a binary operator, which is multiplication for numeric types. It is also the value operator for pointers. So it definitely plays multiple roles. Of course, you're also used to that in other programming languages as well. So it's not That's surprising in a way. Okay. So, of course, we can go one step further. Well, actually, we can go infinitely many steps further, but let's keep it at one at the moment. So, pi itself is a variable. So basically, it has an address in memory, and the address of that variable you can just get by using the ampersand operator. That's pretty obvious. So now I can actually store the address which I get by taking the address of pi. So what does that mean? Well, pi is an integer pointer. So if I want to store the address of an integer pointer, I need a pointer to an integer pointer. So basically, remember the rule, if the type is int, an integer pointer is int star. So if the type is int star, so an integer pointer, and I want to store the address of such a variable, I need a pointer to an integer pointer. So int star star means this is the address, it's a pointer, to a pointer, to an integer. And that's basically the idea here. And we can use that address, of course, basically by using the star operator again. So in this particular case, we would, of course, use for PPI the value which is at the address of pi. That is an integer pointer. So I can take its value, and that would again be I. So that would be 7 at the moment. Okay. Why do we need this? Because this is getting weird. You typically need this when you construct your own data structures. Then you sometimes need to do these kind of things in order to manipulate internal structure of such data structures. But let's perhaps switch to the terminal and actually do this, because it's instructive to actually see it happen. Okay, let's. No idea what was I doing here. Don't remember. Ah, yes, that was a transform. Okay, let's quit this. Let's clear this, and let me do pointers.cpp. And stream. That's for now all I need. Int main. Int I is 5. Int star I pi is I. Int star pi is pi. Okay. Let's see. C dot. I is I. I is pi. That is a good question. I don't know. I never tried. Let's try it later on. I'll try it as soon as I finish this this line. It's an interesting question. I never tried. Okay. Let's see. Okay, so as you can see, the value of I is pretty straightforward. And then indeed we get this rather cryptic stuff in hexadecimal. And these are addresses. And one of the things which is interesting to see is that they don't differ that much. As you can see, the address of my of pi is in fact just after that of I. So basically in memory, we first have 4 bytes that store I, and then we have 4 bytes that store pi. And most likely, we can check, ppi will just be after that. Let's just verify that. Did I make a mistake somewhere? It's possible. In the slide, there was a variable. Yeah. No, what I mean by this sentence, so Shannon's question is about this particular sentence here. So pi is a variable. The value of pi is at this particular address. That's what I mean by that. So the at here refers to the address. So not the value is, but the value is at this particular address. I get the address by applying the ampersand. So that's what I mean. Yeah, it's indeed a little confusing because you really need to see the at. If you read over the at, then this is indeed confusing. That's correct. That's why it's always a good idea to actually do this. I mean, to really see what is where. Okay, I also want to see, just for the sake of the argument, what I just mentioned, the address of PPI. So let's also do that. And then we also need to try what Luc asked. But let's first run this. Okay, and as you can see, can you see it? Yeah, sort of. 88. Okay, let's align this a little bit because this is difficult to read.
You wanted to do the address of pi, right? Not of ppi.
I did want to do the PPI actually. I want to see where that is in memory. Yes. Wait. Yeah, of course. Yeah, sure. I was a little bit confused because I had expected something different, but this is of course hexadecimal. So that's why I got a little confused. So basically, PI is stored at 84. No, sorry, I is stored at. Let's also do this guy here. Okay, so we have quite a lot of them. So basically, the address of I is of course the value of PI. Because that is the address, so those are identical. Notice, by the way, that if I change my code, that these addresses also change. So that's also interesting to see. So as you can see, I and PPI are stored 4 bytes from one another. And then you go from 48 to 50. So that's a jump of 8 bytes probably. Yeah, that would be a jump of 8 bytes. Okay. And that in fact makes sense because addresses are 64 bytes, sorry, 64 bits rather than 4 bits. So you need more storage space to store an address rather than an integer value. Because address space is 64 bits. Okay, so as you can see, things make sense. If I ask for the value at PPI, I should get the contents of PI, and that is indeed correct. That is the address of I again. If I ask for the value at the address which is stored in PI, which is PPI, then I get the value of I, which is 5, and so on. So things make sense. Now let's try one more thing, and that is indeed, let's see whether that actually compiles. So what I want to see, yeah, okay, let's do it here. What I want to see is what is this? Something that does not compile. Okay, let's see what the error message is. Yeah, okay, so you can't do that. Used but not defined. That is a weird error message. I don't think I can get this to work, to be honest. No, this is not a good idea. And that's an L value required. Yeah, okay. But this is an interesting error message that I don't really get. Label I used but not defined. Okay, I'm not going into it now, but I would like to understand why this particular error message is generated. That must be some syntactic thing, which is pretty weird. Okay, but the answer is no, we can't do that. Access no. Right. So this is a bit stuff with pointers. And now, of course, if I want to change the value of I can simply do that by saying, okay, star PPI is 7. Okay. Of course, it helps I don't forget my operator. And then you see that now I is indeed 7 after this assignment. And very similarly, I can also do star pi 9. And again, the value is going to be changed. Okay. So why did we need this kind of thing? And how can this be applied usefully? Well, basically, you will remember that we had the swap function, and that in C++ we could pass the arguments by reference. Okay, suppose that that would not exist. Well, now we know how we can get around it, and that would be the way you would have to do that in C. So just for the sake of the argument and illustration, I'm going to do a pointer swap. So let's avoid swap. And let's say that we swap integers. Now, if I pass in the addresses, now, of course, I can actually change the values, because now I can say, okay, I've got an integer tmp, and I've set that equal to the value of p. Okay. Now, to q, to p, I can assign the value of q, and to q, I can assign tmp. Now, of course, I must pass in the addresses of A and B. And as you can see, if I compile this, you see that indeed the values have been swapped. So basically, I'm passing in the addresses of A and B into P and Q. So P is going to be the address of A, Q is going to be the address of B. So that means that I'm storing the value which is stored at address P in TMP. The value at the address which P points to is going to be replaced by the value which Q points to, and at the address Q points to, the value of that will be replaced by TMP. So this would be the old style C way of doing this particular swap. So that's one reason why pointers in C are very important, because you had to do that if you wanted to pass values by reference to a function. Of course, in C++, we should really not do that because we really don't want to do this in C++ because we can use references, which is much more elegant than pointers. Okay, so RP and Q, in this case, then no copies, no, because they are addresses. They are just locations in memory. They are something like this here, this address. That is what goes in. So essentially, it's the address of the first byte of whatever is pointed to. So if this were, for instance, a vector, a C++ vector can also do that, then wherever that vector is stored, the first byte of it would be the address of that vector. If I would apply the ampersand operator to a vector, that is the semantics. I could pass that to a function and use it as a value. But again, don't do this unless you really need to. Okay. So this mechanism is in fact called indirection. And so in this particular case, we would have double indirection for the star PPI, as you can see. That's just terminology. But there is a famous quote, maybe it's on the slide, yes. So basically, you can solve any problem by just adding an extra level of indirection. That's basically, whoops, that should be indirection and not redirection, I think. Okay, let me verify, but anyway. So that's basically the idea here. So to visualize the double indirection stuff, we have, this was our situation, we had PI, and PI pointed to the first address, or held the first address of the variable I. Okay, so now suppose that that is x74, whatever that is. So basically, if we now have PI, a PI itself is going to store this particular address. Okay. Now we can take the address of PI and store that in PPI, and that would be this particular byte here, which would be whatever. Okay. So that's basically how double indirection works. Okay. So these are the basics of pointers in C and C++. At this point, there is no distinction between C and C++. Okay. Now, we can use either an object or a pointer to an object, and then there is a difference. For instance, let's consider a data structure point, and as you can see, it is fairly straightforward. Actually, I don't quite know why I bothered to make a constructor here, but okay. So basically, it has two attributes, x and y. It has a constructor, which actually doesn't serve any purpose, so I'm better delete it. And then there is a print method, which will simply write that point to standard output. Nothing special. Okay. Now, I can create such an object, and I can simply assign to the x attribute, I can print, etc., etc. Okay. I can also create a pointer to a new point object. And to create a new object of type point, I used new operator in C++. Okay, so that will do two things new. It will create a new point, in this case at coordinates 3.2, 5.1, and it will give me the address of that point. So now P is the address of a point. And if I want to access the x attribute, I have to use the arrow operator, P arrow x. If I want to call a method on the pointer to an object, I have to use P arrow print. So that's basically a syntactic difference. which you have between using attributes or methods of an object, a regular object, that is with a dot operator. If you have a pointer to an object, then you use the arrow operator. It's a little bit weird, but that's basically how it works. So both are what I would term a member operator, in the sense that they give you access to a member, but you've got two ones in C++ and in C, one for the object itself and the other for a pointer to the object. This is a little bit, yeah, it's a syntactic thing. Okay, so do we care about pointers? Well, very often we don't really need to, as I already mentioned, because in C++ we have very nice data structures. We don't often need to build our own. So that is one thing, but there are other reasons to care about pointers anyway. So one of the things which you have to be aware of is that C++ programs, and actually any program, typically uses two types of memory. Of course, it's all in RAM, but it's how that is organized. On the one hand, we have the stack, and the stack, you know what a stack is, we talked about that, is actually used in order to store the context of a function. So basically the function argument, local variables of a function, the return value, and so on. All these things are stored on memory, which resides in the stack. So if a function gets called, you get a new stack frame, and that will store the local variables, the arguments, etc., for that particular function. If you, in that function, call yet another function, that means you get another stack frame where its local variables are stored, etc., etc. If a function completes execution, then its corresponding stack frame will be removed from the stack, and so on. So basically, you start your program with a single frame on the stack, which is, well, it's not entirely true, but the main function. And then, if that function calls a function, you get another frame on the stack. Let me perhaps show you this using a debugger, because that allows you to actually see that. Let me first create a small program, factorial CPP. Don't really need this, but okay. And I've got my factorial function, which is an integer argument. If n is less than 2, return 1. Else return factorial, no, n times factorial of n minus 1. Okay. Function. Result. Result is factorial of 5. Okay, just to make sure that the compiler is not going to simply not generate any code at all, I'm just going to print the result. Okay, let's compile that. And notice I'm adding -g, so I want debugging information in my executable. Again, that does not affect the performance at all. Let's also just give it a name, but it make my executable a little bit larger, because now it contains information about what the machine code, which is now generated, is referring to in the original source code. And this I need if I want to use a debugger. So now I can run this program under control of a debugger, and in this case, this was weird. I don't know what was going on. Factorial exit. Weird. If something is wrong. Anyway, I'll try to continue. Maybe I have to restart my terminal. Anyway, so GDB is a debugger, and you find it, well, you probably have to install it if it's not there, but it's very easy to install just using a package manager, the favorite in your Linux distribution. And this allows me to execute a program step by step, or to have a look at how the program is running. So what I can do is ask for a backtrace, and that actually gives me the frames on the stack. And in this case, there isn't even a stack. Yeah, of course, because I didn't run the program. That always helps. So I want to stop it in line 13 of the main function. So I can just do break 13. Now I've set a breakpoint. And as you can see, that's in the file fuck.cpp and at line 13. Now I can run my program, and it's going to stop in that particular line. It's also indicating it here. Breakpoint has been reached, breakpoint number 1, at line 13. And as you can see, the line is printed, and indeed, it's that particular line 13. So if I do a backtrace now, you see that I have only a single function on the stack, and that is main. So that is my first stack frame in this function. Okay, now on that line 13, there is of course the call to fuck 7. Now I want to step into that function. So I do S for step, and as you can see, I'm now in the if statement of my function at line 4. So basically, I'm now in my function, factorial. Okay, as you can see, it was called with n equal to 5, so that is interesting to know. Let's do a backtrace now, and now you see that there are two things on the stack. The main function is still there, obviously, and as you can see, it's still at line 13, and the fuck function is now the first, well, the topmost frame on my stack. And I'm still at line 4. Okay, n is going to be larger than 2 in this case. So if I do next, I'm going to evaluate that if statement. Okay, so I'm at line 7 now, and I'm in the return statement. But of course, in the return statement, I have a recursive call to factorial. So let's do a backtrace first before I do anything. And as you can see, still 2 stack frames, obviously, but in the first stack frame, so at number 0, I'm now at line 7. Okay, I'll step again to go into the recursive call of factorial n-1. And as you can see, indeed, I'm now in factorial called with n is equal to 4. And again, I'm at the if statement. If I do a backtrace, I've got 3 frames on the stack. So the topmost one is the one for calling factorial with n is equal to 4. The second stack frame is the one n equal to 5. Okay, I can continue that way. So let's do next. step. Let's do next. Let's step. Okay, let's do next. Let's step. All right, and let's do backtrace. So now we have quite a number of functions on the stack. The topmost one is a call to factorial with n is equal to 1. Okay. Then we have below that we have n is equal to 2, n is equal to 3, etc., etc. Okay. So let's do next. And now, of course, I'm in a return statement. The return statement of the topmost. So let's do next again. Okay. And another next. All right. So now I'm back into the function. Factorial is 2. Let's do a stack trace. And as you can see, the top of the stack is now the call with n is equal to 2. The function which was called with n is equal to 1 has terminated. So I can do the same game again. I do next and next, and now I'm back in factorial with n is equal to 3. So if I do a backtrace, you see that now the topmost one is n is equal to 3. So basically at the top of the stack, you always have the function which is currently executing. Below that, you have the function that called that function. Below that, you have the function that called that function, and so on and so on. And so basically, if I put another breakpoint at line 14, I'm now just going to continue to the next breakpoint. So I'll end at 14. If I do a backtrace, only main is on the stack. So basically, this is stack memory. All right. By the way, you also see the addresses here. So basically, these would be the addresses of these particular functions, locations. Okay. I'm going to continue again, and then of course I'm done, so I can quit my debugger. Suppose, just for the sake of the argument, that I make a mistake. You already know what is going to happen. Basically, I'll get I get infinite recursion here. So let me just compile this. If I run it, okay. At the end of the day, I get a segmentation fault. So something is wrong. Okay. I can use GTB in order to try and figure out what is wrong. And in this case, I'm not going to put a breakpoint because I have no clue what is going on, where the problem occurs. So I just run the application. Okay. And then it says, okay, something went wrong. It's starting the program, etc., etc. And then program received a signal, 6 seg, so basically segmentation fault, and that happened in factorial. Oops, n is equal to minus 262,030. Okay, so I can do a backtrace now and see what happens, and then I see that indeed I've got infinite recursion. And basically, this goes on for pages and pages and pages, because as you can see, I have quite a lot of levels of recursion here. Okay, so I want to quit here. Okay, so this allows me to very easily see what is going on in my application when something goes wrong. Okay, yes, I want to exit. All right. So this was just a very brief introduction to debugging with GDB, yeah, you can spend like a day, no, half a day on debugging with DTD. If you're interested in this kind of thing, there's a MOOC on defensive programming and debugging, where among other things, I talk about GDB, other types of debuggers and so on. Also how to test your code. So that might be of interest. Okay, so that's one type of memory. The other type of memory is the heap. And that is actually memory that you manage yourself, or that is managed for you by data structures which you use. And basically that stores explicitly allocated data. And you can do that yourself by using new, or under the hood, of course, something like a STD vector is going to allocate data on the heap. That's where it stores its elements, essentially. So that's basically how that works. And that is managed by the programmer, or in the case of standard vector, it is managed because standard vectors typically do the right thing. And we'll talk about the right thing in a minute. So here's an example, and I've tried this a little bit visual. So we have the stack here, and we are in the main function. So that's the only thing which is on the stack. What is there? Well, all the local variables. So in this main function, we have, of course, data, which is vector of double precision numbers. And we also have a double precision value sum. And we have a value, which is a local variable here in our for loop. So those are the variables which are typically in our stack frame for main. Okay, now as soon as we assign something to data and hence create a new stack frame, that will be assigned, but that goes, okay, that moved a bit too fast, but that doesn't matter. So basically now I'm in my read data function, and there again we have data, and we have value as variables. Okay, so as soon as I execute the data, well, as soon as data gets declared, in the heap, storage space is allocated where the values of data will be stored, and that happens here. So of course, data itself contains the address of that memory in the heap. It keeps track of that. So we have data, the variable data on the stack of read, in the stack frame of read data, and that contains a pointer that contains the address of its values which are stored in the heap. So why is this important? Well, a naive implementation would store the values of data in the stack frame. But remember what happens when a function is finished, that frame is removed from the stack. So where does the data go? Well, what we could do, of course, is copy the data variable in read data into the data variable in main. But that would mean a copy. That's not a problem if a variable is an integer or a float or something like that. But if it's a vector, that's not so pleasant, because that would mean that I would have to copy all the data. Now, I don't want that, because that would take a lot of time. Because as you will remember, memory traffic, memory bandwidth is what is actually going to be a limiting factor for our performance. So just storing all the data of a vector in a stack frame would not be a good idea, because then I would be obliged, I would have no alternative but to copy all that information into another stack frame. I would have to move it from one stack frame to the other. So that's one reason why this is not going to be a good idea. So that's why the designers of the STL vector have chosen to store the data on the heap. Okay, because that actually means that if my variable data goes out of scope, in other words, when it is returned as the result of read data and that stack frame gets removed, the only thing which needs to be copied to the data variable in main is the address of the data on the heap and some other information like the size of the vector and so on. So basically, at the end of the function, we will get that the data in main actually has a pointer to that same location in the heap where read data's data, stored its data. Yeah, there's lots of data there. But you see where this is going. So this is actually the idea why you can do this in a way that is okay with respect to performance. So essentially, this brings us to move versus copy. And at one point in the presentation, I think the section on either user-defined types or classes, I mentioned, well, okay, what I left out is move versus copy semantics. So basically, this was move semantics. The data in my read data function, that's the vector, it was actually moved into the data of main. And the move simply means the data itself, which is contained on the heap, is not copied, but all the meta information, so the size, the address of the data on the heap, etc., that gets copied into the data variable which we have in the main function. So no copy is made. This is a move. And technically, this is called copy elision. So the compiler makes sure that nothing gets copied, that it gets moved rather than copied. And that's referred to as copy elision. Okay, and now, of course, we can use data in our main function. Okay, is that more or less clear? Yeah, exactly. The double value would be copied. Yeah, absolutely. And it's indeed the implementation of the vector template which makes sure that this move semantics happens and that this copy elision is possible. And we'll talk about how to do that in our own classes as well. Because you need to know that if you design your own data structures, then you really need to know this. So we will discuss it in some detail later on. But indeed, a float is copied, a double is copied, that is not moved. There is no point in doing that because a move would be equally expensive as a copy. In the case of simple data types, a copy is not a problem because it boils down to a move essentially. Okay, so memory management, either it's done automatically for you if you use STL data structures. Wow, that was great. If not, you have to do it yourself. So the heap must be managed. The stack is managed automatically. So stack is easy. Heap is potentially a little bit more difficult. So the heap memory you can explicitly allocate whenever it's required, but you should also explicitly deallocate when you no longer need that memory. And that's important because if you allocate something and you forget to deallocate, you've got what's technically called a memory leak. And you're going to be unhappy because if that happens often, the memory which your application is using is going to grow and grow and grow. And finally, there will be no more memory on the heap. The heap will be full. And then, of course, your application tries to allocate more memory. It will fail. Either you handle that gracefully or your application crashes with a segmentation fault. Okay. So if you allocate memory, you also have to deallocate it. Vector allocates memory and will also make sure that it gets deallocated. Okay, so as I mentioned, STL containers do that for you. The constructor is typically going to do memory allocation. For a vector, it's a little bit more subtle. Indeed, the constructor is going to do it, but sometimes also pushback is going to do it because it allocates some memory to start with. And then if you keep on pushing, then of course it needs more memory. It will allocate it. And that will of course be done by pushback. Well, not by pushback itself, essentially, but pushback will be responsible for it. Okay, so that's the allocation part. So where is the deallocation part? The deallocation part is in the destructor. Now, what you also want to do is what also all the STL containers will implement is a move constructor and move assignment. So the move assignment means exactly what we did on the previous slide. So basically what we did, that vector did at the previous slide. So you can assign an object to another object, and that will that will do a move if appropriate. So for instance, if the return value of a function is an object, and you assign that to an object, well, to a variable of the same type, then you get typically a move. And that would be, in this case, a move assignment. So every STL container implementation will have constructors, will have a move constructor assignment, move assignment, will have a copy constructor, copy assignment, and will have a destructor. So basically, this is the rule of 5. You need a move constructor, move assignment, copy constructor, copy assignment, and destructor in order to have proper memory management. Okay, so if you do that manually, the operator to use is new. The deallocation memory is delete. So you would also have to make sure that you have a copy constructor and copy assignment, and move constructor, move assignment, and deallocate memory with delete. So you would also need a destructor. That's what you typically need to do. That creates potential problems. One of them is if you forget to deallocate. So if you allocate it with new and you forget to have somewhere the corresponding delete, that means you have a memory leak. Another problem is a double delete. So if you delete memory that you already deleted before, you get a segmentation fault. And if you don't have move semantics, so if you either don't implement a move constructor and a move assignment, or you don't do it correctly, then you won't have copy elision, and then you will have performance problems, because in that case, C++ will always use the copy constructor or the copy assignment, and large objects will be copied rather than moved, as you would like to have. If you have a copy constructor and it doesn't properly copy the resources, then you will get either a segmentation fault or you get interesting bugs to find. So as you can see, there is a rather long list of problems, and that makes designing your own data structures in a proper way not entirely trivial, but there is some help. So basically, many things can be done with the STL. And of course, if in your own data structures you use STL containers, then of course you sidestep the problem to a pretty large degree. And there's also something which is smart pointers in C++, and this also helps quite a lot. Okay, so semi-automatic is by using smart pointers, and there are actually two of those, in fact 3, but 2 of those are used very often. And one of them is the unique pointer. And that actually means that ownership is unique. So there's only one variable that holds that particular pointer. That's nice because you know that as soon as that goes out of scope, you can do the deallocation. You can call the destructor. So you don't have to do that. The unique pointer knows that as soon as it goes out of scope, it can call the destructor of whatever it's pointing to. So that's very easy. So it will auto-delete whenever its owner goes out of scope. And we'll see this in action later on. The second type of smart pointer is a shared pointer. And that means that you have shared resource ownership. So you can have multiple shared pointers that point to the same object. And then that means it will be auto-deleted when the last owner goes out of scope. So now you might wonder, well, okay, why don't I always use shared pointers? Because if I have a single shared, it will also go out of scope as soon as the owner goes out of scope. So what's the point to have 2 of them? Well, shared pointers, of course, do more bookkeeping and hence are a bit slower. And also, the semantics is different. Because if I use a unique pointer, I'm really making clear to myself and the compiler that there is only one unique pointer to that certain object. No more, no less. So it's single ownership, while with a shared pointer, no one has that guarantee. There may be pointers dangling somewhere to that object without you realizing. So that's why if you can use a unique pointer, it's the better way to go. You can kind of compare it a little bit to owning a car versus using Cambio, so basically shared car system thing. So it's a little bit the same. Okay, so basically you need to track the number of owners at any given time for a shared pointer, and if one of them goes out of scope, the number of owners is decreased by 1. If the number of owners is 0, then it can auto-delete. That's how that works. You have a third kind of thing, which is a weak pointer, and that's for temporary resource ownership. So that is something that you would use if, for instance, you have cyclic pointers. Then a weak pointer is very useful, because otherwise, yeah, you would have you could never delete that particular objects because they form a cycle. One refers to the other and refers back to the previous one, and yeah, there will always be some owner. It will never go to 0. So if you use a weak pointer, that does not increase the number of owners. And you construct those from shared pointers. So basically, they are not counted for reference count. So that means that if I create a weak pointer out of a shared pointer, the number of owners of that shared pointer is not going to increase. That's the semantics here. And basically, if you want to use it, you convert it back to a shared pointer. Okay, so it can be used either to model temporary ownership or to break cyclic references. For instance, if you have a graph and you implement that using pointers, which is one way to do it, there are other ways, then you would definitely need weak pointers to avoid cyclic references. Okay. All right. So that is also a chapter in Strassrup. What I added was C-style pointers. Why did I bother? Basically, because it's on the one hand useful to know, and on the other hand, if, for instance, you use GSL, so the GNU Scientific Library, which we discussed yesterday, then you're writing C. And it makes extensive use of pointers. So if you don't understand C pointers, you will have a hard time using something like GSL or any other C library, because yeah, just due to the fact that it's actually C, you can't use C++ pointers. So you need to understand and be able to use C pointers. I also added some slides on memory management, so heap versus stack and so on, because it's useful to know. Okay. Of swapping vectors without copying. Yeah, well, the code which I showed, this is an example. So this is an example where you would say, well, okay, what is happening? Read data is going to produce a vector. So now there are two possibilities. If I do the assignment to another vector variable, either the data produced by read data is copied into the data in the main. That would be copy assignment. You hope that's not going to happen. So basically what you hope is that the data which is produced by read data is going to be moved into data. Let's experiment a little bit and see how things pan out if you do that in practice. Because slides is one thing, code is a different thing. The usual IO stream. Vector on the function. Well, I'm going to use an alias because I don't want to type vectors, std vector, etc., etc. So I'm using data is std int. That's good enough. And then we have a function that produces data. I don't know. And the only thing I want to pass in is a size t of which is n, and that's going to be the size of my data. Okay, I'm going to create a new data vector. And I'm immediately going to make it a vector of size n. And then I can just initialize. Okay. I can just push some data to it. Let's say int is 0 is less than n. And data pushback data, and something is odd with my indentation. Okay, so that's my function, and as you can see, it just creates a new vector. Okay, now I've got my main function. And I'm going to have a new variable, let's say d1, and that is initialized with init data length, whatever. Okay. Now let me also, because again I'm lazy, I have a function show data, and that's a const data ref. Which of course is just going to print to std out. Did something stupid apparently. Why is it unhappy? Audio stream. Ah, yes. I've got a single quote rather than a double quote. That should be better. Okay. Yeah, indeed. Right. So this of course should compile without any issues. No surprises. Okay. All right. Now let's have data e2, and I assign e1. Okay. Let's first. Okay, let's make this a little more sophisticated. All right. Then I can do this actually a little bit more elegant by. Always annoys me a little bit that I have this trailing space, which I now can avoid. Nitpicking, but all right. So this is a little more convenient because now I can actually show. Remove the show. Called show. So now I can show d1. d2. Okay. And of course, I don't think there will be any surprises when we compile and run. Same thing, no problem. Okay, but now the question is D2 a copy of D1 or whatever? Well, it's very easy to find that out because what we can do is change a value in D2. for instance, the second value is replaced by -15. And now again, I can show you both D1 and D2. And as you can see, D2 has been changed, D1 has not been changed. So basically, what is going on here? We have, in this case, we have a move, because the original data in my function initData is a vector, and that's been returned as the value computed by initData. So in the beginning, there was only the data in function initData. As I already mentioned, its data got stored on the heap. And what happened here in this move constructor, because now it's actually a move constructor, I'm going to move that address where the data is, which resides in our function. I'm going to move that into our D1. So D1 is created by the move constructor. Now, in the second line, in line 25, we create D2 based on D1. And this is going to be a copy constructor. So basically, D2 will get all the properties of D1 and also a copy of its data. So line 24, move constructor, line 25, copy constructor. And indeed, you see that one is a copy of the other. They're not identical anymore. So that's basically how that works. So I could create another vector, D3. Yeah, if I type 3, that would help. And I'd also, I've not initialized this one yet. Okay, and then I can do D3 is the again. And let's also show D3 now. Okay. File mirror. And you see that D3 is indeed similar. It has similar values as D1. Question is it a copy or is it the same thing? So let's see. Let's move. Let's modify D3. Let's say that the second element is going to be -39. Okay. Let's show D1 and D3. And as you can see, D3 has been changed, D1 is untouched. So again, D3 is a copy of D1. And now in this case, this is copy assignment. So the values which are stored in D1 are copied into a new vector, well, a vector which already exists is D3, but in the vector D3 by the copy assignment. So that is our third thing. We have move constructor in line 24, copy constructor in line 25, copy assignment in line 32. And we don't have a move assignment here, but we can actually create one if we want to. So let's say D4. Now I can do an explicit move. Don't do this at home. I can use std move, and I do this on, say, D1 again. Okay, so let's see what is in D4. And as you can see, D4 is, oh, wait, this was stupid. That's impossible. But okay, so in D4 is now indeed the same data as in D1. Or is it? Let's have a look. And what I'm doing now is in fact really, really dangerous. But let's see what happens. As far as I know, the STL will do kind of the right thing, although it is implementation dependent what happens. Let's see. Okay. E1 doesn't give anything. No, indeed, because now we actually have we have 4 things going on. What happens here in line 39 is in fact a move assignment. So all the data out of D1 is moved into D4. So D1 is actually left in a state which the C++ standard doesn't specify what should happen. So actually I shouldn't use it anymore because I've moved all the data and all the stuff out of it into D4. So later on using show data on D1 is in fact a very stupid idea. I really should not do that. I just wanted to see what happens. So in C++, in the STL, if you have a proper implementation, then you won't get a segmentation fault. But yeah, don't do that. I mean, it's really not a good idea. What happens is that the vector D1 will actually have size 0, so it's kind of an empty vector. But again, you don't need to do that. It's just politeness. The C++ standard doesn't specify what you should do, because after you did a move, the original object can completely vanish. And that's indeed what really, really happens in the function. So after the move, in this case a copy move into D1, the value which was returned by the function is destroyed. So the metadata in that vector has been copied into D1, and whatever is returned here goes out of scope and vanishes. So 24 move constructor, 25 copy constructor, 32 copy assignment, 38 move assignment. So we have all 3 of them. Okay, all 4 of them, sorry. Where's the destructor? Well, the destructor is basically everywhere at the end of the function main. So after the return, the destructor of D2, D3, and D4 is going to be called automatically because those variables go out of scope. They have a destructor defined, and that destructor will be called as soon as the variable goes out of scope. The one on D1 is not going to be called because the one on D1 is also going to be called in this particular case. Okay, is this more or less clear?
So when I would want to void swap, if I would want a void swap function that swaps D1 and D2 without copying all their values, how would I do that?
Then you would actually use the swap function, which is in standard library. because there is a swap in the standard library which does this for you automatically.
All right, but say I want to write that function
Say you
myself.
want to do it yourself. Yes. If you want to do it yourself, it's very easy. And in fact, let's just do that. Let me, just to make sure that no horrible things happen, just let me take out the move thing here. Because that is suddenly using D1 afterwards is really a very bad idea. So I'm just not going to be tempted to do that. Because if I do by accident, then all hell can be loose, and I don't want to go there. Let's do a swap. D1 data ref D2. Okay, so I've got a temporary data, and I'm going to do an assignment. Well, I can do it this way. To do an assignment. Okay, now in D1 store D2. Okay. Now D2 is TMP. Okay, so this is the naive way of doing this. What would happen? Let's have a look. So we pass D1 and D2 by reference. So absolutely no copying, moving, or whatever is going on, because basically D1 is just another name for whatever I pass to, whatever variable I pass to the swap function. Okay, so nothing happens when, or nothing interesting happens when the swap function is called. Then we have the first line 15, and we create a new data object. So basically, this is going to be a copy constructor. So I'm going to make a copy of the data in D1 into the new TMP. Then in 16, we have a copy assignment. And in 17, we have a copy assignment. So this is going to work, but it's not going to be particularly fast. So what I could do is I could use a move here, because the data in D2 can just move to D1. And similarly, the data TMP can also move to the data in D2. And good measure, and also do a move assignment. So now basically I have 3 moves, I have no more copies. Of course, this is a little awkward to do, because you must really realize what is going on. So that's of course why in the standard template library, there is in fact a swap function, and that will do the right thing for all STL containers and so on, also for all primitive types. So the floats and the ints and the doubles of this world. So I would definitely recommend to use that if you need the swap function. I always give the swap function example, but somewhere in the slides I should add that there is this std swap in the standard library, which actually does the right thing. So I would guess that if I were to time this, swap version, that it would be equally fast as the STD swap in the standard library, because that will do the exact same thing. It will do 3 moves. Okay. I would suggest we have a break, and then we have a look at actually implementing our copy constructor, move constructor, copy assignment, move assignment, destructor, and so on and so on, in case you want to build your own data structures. But are there any questions at this point? Okay. If not, let's have a break, and let's resume at 11. Something. All right. Let's get some tea or some. Okay, let's resume. I'll share my screen again. Right. So let me return to the code. And let's look at so I need to think for a second where I have an example. That would likely be in classes somewhere. Not really. Bytes. Yes, object lifecycle. So let me go in there. And this is an example of the lifecycle of objects. Yeah. Okay, so let me show you what Gadget does. It doesn't do much, but it shows you copy containers and so on. And obviously, I'll need a bit more screen real estate here. Let me perhaps just close this guy. Okay, let me also increase the font size a bit. Okay, that's better. So basically, this thing doesn't do much in the sense that it actually doesn't do resource management, but it shows you, it's designed to show you when a copy constructor, well, an ordinary constructor, a copy constructor, etc., copy assignment, and so on, are actually called. So the gadget itself is pretty simple. It actually has just two attributes, value and ID. And just for the sake of the argument, there is a global variable, in a sense, which is ID counter, and which, of course, I'll use in order to ensure that I get a new ID each time I call this thing. Okay, so this is the default constructor, the standard constructor. If you create a new gadget without specifying anything, you will get a gadget with value 0 and with an ID counter which is incremented by 1. This is just to make sure that each time I create a gadget, or that a gadget is created, that in fact I'll get one with a different ID. I can also create a gadget with a given value. So basically, in that case, it's nearly the same thing, except that rather than having value, it's going to be having 0 as a value, it's going to have value as a value. And actually, I could implement this constructor by using this constructor as well, but whatever. I just make the difference because then I can see I have a different implementation. Anyway, so these are constructors as we know them by now. The next one is going to be a copy constructor. So as you can see, as an argument, it takes another object of type gadget, and it's a const ref. So basically, the object which is being passed in is not going to be modified. No, indeed, because I want to copy it. Now I'm cheating a little bit because actually the semantics of a copy constructor says that it should really be it should be the same thing as the original object, and nevertheless I'm going to give it a different ID counter. So that's just to make very clear. It's not really semantically correct, but okay, it will work. But that's to make very clear that the object which is constructed is a new one, and I can distinguish between the one which was used by the copy constructor, so other, and the one which is being constructed, because it will have a different ID counter. But as you can see, I'm going to copy the value of other into the value of the object I'm constructing. So that's basically the idea here. And as you can see, we explicitly do the ID thing and so on, so that we can see what gets copied from where. Okay, very similar is the copy assignment operator. As you can see, the assignment operator is the equality sign, and I'm going to overload that. It's going to return a reference to a gadget, and it's going to take as an argument a reference, a constref, to another gadget. And again, of course, for the object on the left-hand side of the assignment operator, we copy the value into its of other into its value attribute, and again we are going to return some stuff, and of course we have to have a reference to a gadget as a return type, so that would be the value of the dispointer. So this is something we also didn't discuss, but if you have a constructor, or if you have an object in general, also an arbitrary method, in fact, there is a pointer to the object itself available in the method, and that always has the name this. So that's automatically there. So in this case, I want to return not a pointer, but an actual object, reference, and hence I apply the star operator to get the value of that dispointer, so the object itself rather than its address. Okay. Up to this point, I would say fairly much okay. Now we have yet another constructor, and this is a move constructor. You can see that because basically there is no const here, and there is a double constant. And that means that other is going to be moved into the new gadget. So again, we fiddle a little bit with the ID, make the ID go up, and then we move the value of other into the value of the new object. Now, of course, in this case, since value is just a simple integer, the copy is the move. I mean, the move is the copy, it's the same thing. If, on the other hand, value would be something a bit more sophisticated, like for instance a vector, I would use std move here to move other value into value. Maybe I should change the example to actually do that. Okay. Again, here we have a move assignment operator. Again, look at the signature. So basically, it says that the value is moved, and then it prints some stuff, and it returns this value. Also note that there is a no except here. So move constructor and move a move constructor and the move assignment should never throw an exception. So that's why it's also explicitly declared that this is a no except. And that's here at the end of the line. Okay, last thing is the destructor. So in this particular case, of course, there is nothing to destroy, because at the end of the day, we simply have just an integer value. But if I would have used new in any of the constructors, then I would have to use a corresponding delete in my destructor. The destructor is, the signature of the destructor is very simple. It's just the name of the class, but preceded with a tilde. Tilde, which is also negation, a bitwise negation, it is kind of a negative thing, over negating things, so hence that notation for the destructor. And that is the function that will be called when a gadget goes out of scope. Okay, then I have some silly things here, an ID and a greet method, whatever. All right. So, rule of 5, I've got my copy constructor, line 20, copy assignment, line 25, move constructor, line 32, move assignment, line 35, and finally, destructor, line 44. Okay. Gadget.cpp. It does quite a lot of stuff. So basically, there are quite a number of functions. So there is a greet by value. And as you can see, what I pass in is actually an object. So this is going to be call by value. Here I pass a reference to a gadget. So this will be called by reference. Get gadget is going to create a new gadget. It's going to create a gadget inside of this function, and it's going to return it afterwards. And then we also have a method get lots of gadgets, which will create a vector which holds gadgets, initialize those, and return those gadgets. Okay, note I'm using an nplace back here, which I already did with a point example a couple of well, some time ago. Now, in my main function, I'm going to do a lot of stuff. As you can see, it's even more than a page. So let's split this again. Because I also want to execute this, so I'm going to decrease the font size a bit, hoping that you can still read this. Is this still okay? Okay. And this I'll increase a bit. And need to go to source files. That was in user-defined types, in object lifecycle. Okay, let's see. That's a classic make file. So let's make. So now I can actually execute most gadgets. Yeah, gadgets.exe. It doesn't take any command line arguments, I'm guessing. So let's go to the beginning. Okay, so I'm executing this. As you can see, lots of stuff happen, and I'll just go to the beginning, and we'll compare the output with what happens in the main function. All right, so declaration with initialization. Without initialization. No, with initialization. Okay, so first we call gadget, and that would be the constructor which has no arguments. And indeed, object number 1, our first object, is indeed called using the constructor with no arguments. So that would be the result of line 34. Okay, in line 35, we actually call a constructor with an argument. And indeed, that's a new gadget, gadget 2. Now, I do a copy constructor. I create gadget 3 based on gadget 2. Okay, and indeed, as you can see, copy gadget 2 with value 5 to gadget 3. So indeed, here the copy constructor has been called in line 36. All right, and then we start with assignment. And we just assign G2 to G1. Okay, so that should be copy assignment. Okay, indeed, copy assign gadget 2 to gadget 1. So now in this case, gadget 1 and gadget 2 will both have the value 5, but of course they have still a different copy ID. Okay, then, so this is copy assignment. Then, let me see, where are we? Yeah, here. So now we do function calls, and we have greet by value. So greet by value was a call by value function. Okay, and as you can see, when we do that, then there is a new object created. So this really proves that when you do call by value, that you get a copy of the object, whatever it is. So indeed, in this case, the copy constructor is called, and we get a new object with ID 4. And then we have greet value by 4, etc., etc. It does the greeting, and then it destroys the object, object 4. Why? Because the new object 4, new gadget, was created because we had a call by value. So basically, as soon as the argument of the function goes out of scope, the constructor can be called, and indeed it is called. 4 was created when the function was called, 4 gets destroyed when the function completes. Okay, if we do the same thing, but now we use greet by reference, then you see that we don't get a copy, we don't get a destruction. No, indeed, why would we? Because we are just passing in a reference to object 1, to gadget 1, and that does not get copied, nothing gets destroyed, and so on. So this proves that this was really call by reference and not call by value. Okay, then we have the get gadget function. So that would create a local gadget with the value which is specified, so with value 19, and it would return that as the result of the function. So what is happening? Indeed, you see that you get a new gadget created with ID 5 and value 19. And that's good. So we just print that we are in get gadget, no problem. And then, as you can see, gadget 5 is returned by get gadget. So if we just print the ID of whatever was returned, you see that it's indeed that particular gadget. So this was basically just copy elision. It has just been initialized into the variable which we have here. So gadget 4, confusingly, in G4 holds is in fact 5. But notice that no copying has taken place. Also, no move has taken place. So under the hood, copy elision has happened, and it was simply very silently moved into gadget, into the variable G4. Okay. So if we add to a vector by pushback, so that's the here we are using the we create an array of gadgets, and we reserve 3, and we do a pushback. We do that here. Then let's see what happens. So that is what's happening here. So each time here, we actually have an iteration of that for loop. So in each for loop, we are in fact creating a new gadget. As you can see, gadget 6 is created with value 0, indeed, because I goes from 0 to 2 inclusive. So we create a new object with ID 6. We move that object to a new object in the vector, and we destroy 6. We create 8, move it into the vector to an object with ID 9, destroy 8. Create 10, move it, destroy 10. So as you can see, if you have sophisticated, well, non-trivial objects in a vector, and you use pushback, you in fact get a copy. So basically, this is not something you want to do. And that's why an emplace is much better, because as you can see in the emplace, the constructor is called, but no move, no copy, no destruction, whatever. So the object is directly created into the vector. So emplace back is definitely something to use if you're concerned with performance. Meanwhile, we are here. Okay. So if we have the get lots of factors thing, oops, where am I? Get lots of factors. Where is get lot of factors? Here. Get lots of gadgets. So basically, as you can see, again, we just used an emplace back there. So we just get object creation with the default constructor, no move, no copy, no nothing. Okay, then we are at the end of our main function. So clean up, and indeed, as you can see, everything that needs to be cleaned up is cleaned up automatically. The only one which does not get cleaned up, well, there are a few which don't get cleaned up because they have already been cleaned up, but everything that was still in scope now gets destructed. And that's because I have my destructor defined. Is this more or less clear? All right. I may have because this is nice to show the life cycle, but it would also be nice to show you an example of where that is actually being used. I have an example of a tree somewhere, but where is that thing? Probably glasses, I think. No. In tablets. That's a good place to store it. Where's my tree? Not here either. So in pointers. Yeah, okay, yeah, makes sense. Okay, let's have a look at this. So this is an implementation of a tree, and maybe, but I don't quite remember, I've actually kind of done the right thing. Let me have a look. Because it's a while ago that I wrote that code. And let's again this for a second, otherwise it's too hard to read. So no, we don't seem to have copy constructors and so on. No, unfortunately not in this case. No. Yeah, that's a bit unfortunate. I at some point have to make a less trivial example of this lifecycle thing where there's also some data involved. That's more interesting, but I don't think I have one handy. I don't think I did that here either, but let's check. No. No copy constructors, whatever. Okay, so yeah, that's now on the other hand, if you just look in a tour of C++, there is actually an example where vector is kind of like, no, not vector, a sort of array is implemented using on the one hand templates, I think, and on the other hand also with copy constructors, move constructors, copy assignment, move assignment, destructor, and so on. So there is a very nice example in there, but I don't think I implemented one here myself. Anyway, so one thing which is very important to know, and that's really crucial, that is that if you do copy constructors, move constructors, and so on, you always have to do everything. So basically, in order to for things to work correctly with move semantics, copy semantics, and so on, you do have to have all 5 of them. So copy constructor, copy assignment, move constructor, move assignment, and destructor. You have to have all 5. So in a way, it's to make everything work properly, it's either all 5 or none of them. So what you can have, of course, a class which just has a copy constructor and nothing else, but then don't expect that things like copy elision will happen automatically. So things like that will only happen when you have all 5 implemented. So that is often referred to as the rule of 5. You either have 5 or you have none. Again, you can have a class that just has a copy constructor, no copy assignment, no move constructor, and so on. That's entirely possible. If you don't need copy elision or whatever, if you don't care about move semantics, you don't need to implement it. But remember, you won't get the benefits of these things with respect to performance and memory management. Okay. So perhaps let's return for a second anyway to that tree class. I have the pointers now, I remember. Okay, so let's have a look. The things which I don't need. So basically, let's first have a look at nodes itself. But as you can see, it's a class with a number of private attributes, and it's templated. So basically, that means that in a node, I can store arbitrary data. Value is the value of the node, and given that it's parameterized, I can store any type of data I want. So a node, in this case, it's a binary tree. So a node can have a left child and a right child. And as you can see, those are pointers. Now, the node constructor itself just takes an ID and takes a value, very easy, and it will assign a non-pointer to the left and the right attributes. So if I just create a node, it's not going to have children, and hence I denote that by having those pointers set to the null pointer. A null pointer is a special value. It's a little bit like, okay, this has no special value, this has no real value assigned to it. Okay, I get some accessors for ID, for value, and so on. Some setters, value to change the value. So nothing special happens here. A Boolean function whether the node has a left child and a right child, basically just by checking if left is not a null pointer, then it has a child, otherwise it doesn't. And then an accessor for the left child, etc. Okay, setting the left child and so on. So nothing much special happens here. There is a toString method, which basically allows me to serialize a node to a text, and basically toString implementation and overloading of the send-to operator and the destructor. So the destructor is interesting in this case because I have a pointer, and of course at some point that is going to be created with new. Not here in this particular code, but you will see it in the main function. And basically that means that if there is a left child, it should be deleted. Basically, its own destructor of the left child should be called, and that's done by delete left. And if there is a right child, it should also be deleted. So this is a non-trivial destructor. Okay, let's have a look at the main function. Where's my main function? No, I'll just have to check because I don't remember what the main function is. These are header files. Okay, so that would be 3CPP. Okay. So this is the main function. As you can see, it's pretty straightforward. I have a function to build a tree, and it gets a pointer to a parent, and then a certain depth. Okay, so this is a templated function in the sense that, again, I can just choose whatever type for the values I want. Okay, so if the depth is 0, then of course I don't need to do anything and I can just return. Otherwise, I get a parent ID, and then I add and the value, and then I'm going to create a child. And as you can see, I use new. So I'm creating a new object of type node. And I just use the parent ID, add 1 to it, and I also add 1 to the value. I do the same for the right child, only I add 2 to stuff. Notice parent is a pointer, so I have to use the arrow operator to apply methods, to call methods on them. Okay, as soon as I've got my parent and I've got the left and the right child added to it, I'm going to call this build tree function recursively, but now on the left child and the right child, and of course I decrement depth by 1. And that will get me a tree. So in the main function, I just create the root node, which in this case has the value 0. It's floating point actually. So the floating point value 1.1 and ID 0, and then I'm going to build a tree. I'm going to make a string out of it, and copy that to standard out, or show that on standard out, and I'm going to delete my root tree. So remember what the destructor does. It is going to call delete on each of the children. So if I call delete on root, it will call delete on both of its children. Those children will call delete on both of their children, and so on. If a node has no children, the destructor is not going to do anything. Okay, so that's my node. Let's create a new tab, because I don't want to destroy tabs all over the place all the time, so I'm just going to move there. So that would be source code pointers3. Okay. Full directory, move to it, cmake, cmake. Okay, there are warnings. Unused, yeah, okay, unused parameters. Yeah, I should just remove them because that's silly. Yeah, all the same warnings. Yeah, I'll remove those because that doesn't make sense. All right, then let me run this. So that's likely to be tree.exe, and then you see that indeed we get a tree. This is the root node, left child, right child of the root node, left child, right child of node number 1, etc., etc. Okay. So this is with raw pointers, which frankly I would not recommend to do. Can we do better? Yes, we can. So basically, I would recommend this approach here with unique pointers. And basically, as you can see, not that much changes, except that rather than having a raw pointer node t star, we get a unique pointer node t. Okay, so nothing much changes except left. Here you get something different. So now, rather than returning a pointer to the left child, we're actually going to return a reference to the left child. And we do that by actually returning the value at left. So left itself is a unique pointer. If I do get on that, I get the address, the row pointer it refers to. If I apply the star operator to that, I get the value. And I'm returning a reference to that. So this makes life actually a lot more convenient. Similar, of course, for right. And here is also something more interesting. So set left now takes a reference. Takes a unique pointer to a child, a reference to that, and it's going to move that unique pointer into left, which is also a unique pointer. So since this is unique, it means that I can simply move it, and the ownership of the node is going to be transferred from the calling context to this node which I add a child to. So the ownership is always with the node that contains the children. Okay, similar for right, so nothing much changes here. Let's have a look at the main function. So this is the implementation with unique pointers. So I'm going to create the node as root first, okay, and then I'm going to use build tree. So build tree now actually just takes a node reference, no problem, and it will create a left child by making a unique pointer. And then I'm going to set the left child. So after I've set the left child, I can't use the variable left child in this function anymore because it has been moved into the parent's left child, the parent's left underscore attribute. Similar for right. So indeed, I'm doing the recursive call now not on left child, but on parent.left. Okay, and in a way, this is much more convenient because now I can treat the result of the left method just as any object. Also, my parent here is in fact just an object, not a pointer to it. So I would argue that this is more convenient to work with. You can do the same thing with shared pointers. Shared pointer stuff. Yeah, it's node shared pointer. Okay, so this is an implementation with shared pointers. Now, as you can see, this changed. This is now shared pointer rather than unique pointer. Okay, no problem. So the interesting thing, of course, happens now again at left and at right. So basically, a shared pointer is now returned as left. So that means that ownership is on the one hand in the node, and on the other hand, there will be another owner in the calling context. So the reference count will go up by 1. Set left, we're assuming a unique pointer, and we're going to move that into the left pointer. So that remains the same. Ownership is transferred from the calling context into the parent node. And similar for right. So nothing special happens here. So let's have a look at the main thing. So again, we're going to make a shared pointer now for the root. Okay. And we built a tree based on that shared pointer. So in the build tree function, we get a shared pointer as an argument. And of course, we create a left child, again with unique pointer, because we want to transfer the ownership of this into the tree, into the parent node. And that happens in set left. Similar for right. And again, of course, we use tree left and tree right in order to build the tree. So this is also possible. The advantage of that is that you can actually share nodes between trees, for instance, or you can share nodes in other contexts. It's possible. But frankly, I prefer the unique pointer approach where you work with references and ownership of a node is unique in the tree. So the tree is the only thing that holds a reference to the node. And that, in fact, is in a way much more elegant because then as soon as the tree goes out of scope, all the nodes get destroyed, and that's typically what you want to happen. Okay. All right. Maybe let me, is this more or less clear? There is another example of your own data structure. I think, yes, there is a double linked list implementation here as well. So basically, if you're interested in that, you can have a look at it as well. Okay. One thing more about pointers, which I already pointed out before, but said, well, okay, we'll return to it because now it's a little bit too early. Let's have a look at that helps a little bit to clear up things. At this runtime versus compile time. Okay, so what have we got here? Yeah, I'm not going to use this example. I'm going back to the thing I already showed you because I think it's more interesting to have that example. This is okay. So classes quadrature. Yeah, that's the one. So you remember this example? We had a program that could do quadratures, and we could choose on the command line whether we wanted the Gaussian method or a Simpson method. And the problem is we need to decide that at runtime, or rather we want to decide that at runtime. So let's have a look at the main function again, because the implementation of the classes as such doesn't really matter. It's not that interesting in this context. In this context, we're interested in the main function. So let's have a look at the main function. And as you can see, I check the command line arguments, and I just check whether I have the Simpson method or the quadrature method. So now the problem is I need to somehow make sure that I can store, that I can deal with either that I can either do the Simpson method or the Gaussian method. And as you might recall, what I can do is I had my class quad, which is here, and this doesn't do much. Well, it doesn't do anything at all, basically. It just says that there is a virtual function, and virtual means that it's declared here, but it's not implemented. Okay, so this is a method, sorry, this is a class I cannot create objects of, because as long as I have a virtual function, it's a function which is declared but not defined, I cannot create an object of that type. Okay, however, this is a base class, and the only thing it's in fact supposed to do is to ensure that any class that inherits from it should implement this method integrate. Okay, and one of the things that I have to do if I have a virtual class or an abstract class, I have to have a virtual destructor. This is very important because otherwise memory management is not done properly. So of course there is nothing to destroy here, so I just set the default destructor, but I have to declare it. Okay, and you will remember that, for instance, our Gaussian class just inherits from quad, and it then implements the integrate method, and it indicates that it does so by putting override here. And of course, in the corresponding CPP file, there is the implementation of, in this case, both the constructor and the integrate method. Okay, let's return to main. So that means that the Simpson method and the Gaussian method, Simpson quad, Gaussian quad, are both special cases of quad. They inherited from that class. So I can create a pointer to quad, and that pointer to quad can either be a pointer to an object of type Simpson quad or of type Gaussian quad. So I just specified that I have a unique pointer to a quad, whatever that is, and then depending on the command line argument, I make a unique pointer for a Simpson quad or for a Gaussian quad. So quad is now a pointer to either a Simpson or a Gaussian quad. And then I can just use that pointer. So in this case, I'm going to get the raw address of my quad function, of my quadrature method rather, and pass that into the compute quad function. And that is going to take a pointer which can't change to an object which can't change either. So hence const quad pointer const. And this is my pointer. So now I can simply call the quad method. It's a pointer, so I need to use the arrow operator. So that's basically the idea here. And this is a case where I do have a unique pointer, but I'm not passing that unique pointer to the quads, to the compute quads function. What I'm passing is a raw pointer. Why am I doing this? Well, I could pass the unique pointer. I could put here const quad pointer reference, no, not reference, quad pointer, etc., etc. But in that case, I would transfer ownership. I would transfer ownership from main to my function. Given that it's a unique pointer and ownership has been transferred, as soon as my function ends, my quad object gets destroyed. So if I wanted to reuse this quad object later on, to compute the same thing but for a different function, I would of course be working with an object that has been destroyed. And that would of course kind of be a bit of a big problem. So I shouldn't do that. And hence I'm using a raw pointer just as just to make sure that I can work with it. It's const all over the place, so I can't mess it up anyway. And I can simply I'm using my unique pointer here. And as soon as quad goes out of scope, the destructor is called. Okay. Is this more or less clear? Probably, sort of. Okay. I would like to give you one more example of something slightly different. So let's go to templates and to duck typing. So this is actually the same example as the same problem being solved as before, but now differently using templates. Remember what we wanted to do. We wanted to be able to apply quadrature methods, and all quadrature methods, well, all quadrature things should have this integrate method. And to do that, we had a virtual base class, so an abstract class, quad. and the Simpson quad, the Gaussian quad, the whatever quadrature method that I choose to implement must inherit from this base class. So that's one way to do it. The other way to do it is using what's referred to as duck typing. And that just means that, in fact, the only thing which I require from something that computes a quadrature is that it implements the integrate method. That's all that interests me. All the rest is, in fact, irrelevant. How I create such an object, I don't care, as long as it has an integrate method. So that's a little bit that is the spirit of duck typing. If it quacks like a duck, if it flies like a duck, if it swims like a duck, it's most likely to be a duck. I'm only interested in the fact whether it can swim, can fly, can quack. Then it's fine, I'll consider it a duck, whatever it is. That's basically the idea of duck typing. So if we have a look at the code here, you see that we have, again, a number of things. We have a Gaussian quadrature and we have a Simpson quadrature, but we don't have a quadrature class. Well, we don't have a header file for quad as we had before. So let's have a look at Gaussian quad. And as you can see, it is a class again, but there is no base class. So this is not an inherited class. It's just a class which just is there. Nothing, it has no relationship to anything else. Okay, so it implements an integrate method. The signature of that method is an integrand, which is a function that takes a double as an argument and returns a double, and two const double values. That's all it does. And the implementation is the same as before. I'm not going to show it. Let's take the Simpson class. And as you can see, again, no base class. It doesn't do anything special. The only thing it does is, again, implementing the integrand, the integrate method with the exact same signature. Integrand, double, double. Okay. Nothing very interesting. So let's have a look at the main function. So this is now the main quad. And in this case, I'm using templates. So I've got a function at line 12, or line 13 if you want, which is in fact a template. And as you can see, it has a type name T as a type as a template parameter. And as you can see, the type which is free is the type of the quadrature object. So we have T quad. And that's the only place where T occurs. So basically, we just call quad.integrate. So that means that I can apply this template, and as long as the T class is an object, well, is a class for which the objects implement the integrate method, I'm going to be fine. So basically, now in this implementation, we're just going to have the Simpson quad method. I'm just going to create a Simpson quad, and I'm going to compute quads. So this is slightly different from before, but basically the idea is to show you that the principle of duck typing. So as long as a certain pattern is, or no, let me rephrase that. As long as a type has certain properties, I can actually pretend it's all the same thing. And this is, of course, somewhat unsafe in the sense that I could try and call quads, with something that does not have an integrate method. In that case, of course, the compiler is going to complain because this is compile time. So basically the compiler is going to check, okay, you are calling this function with T and that squad. Does squad have an integrate method? So is there in the implementation of your class an implementation of integrate? If so, no problem. Then the right code will be generated by the compiler. If not, the compiler is going to give you an error. The problem with that is that the errors are going to be fairly awful. It will be very hard to interpret. And that's why in C++20 you have the notion of concepts. And then you can set requirements on T and, for instance, specify that this is only going to be applicable if T actually has an integrate method with a given signature. Okay, so still the compiler is going to complain, but you will get a much more meaningful and much more easy to interpret error message. And that's where concepts come in. I have a small example, I think, somewhere, but it's not a sophisticated one. Let's see what I have. Yeah, that is likely not going to be very exciting. No, not really. So basically this specifies that in this case our X in fact has to be a type which can be converted to a string. So this is not particularly exciting, but basically the std convertible to, that is a concept. And this requires, this can also be used with templates, this requires a mechanism, ensures then that the compiler knows what you expect if this template, or in this case this type inference, is being performed. And you will get some more meaningful error messages. So let me perhaps show that a little bit. Let me clean up somewhat. Out. All right. Oh. So let's have two. And we have const star x. And just so this is the function without any requirements. And we have a call function with so this actually will work, and nothing much interesting is going to happen. What I could do is send this to standard output. Right. So my compiler is not going to be, well, my editor is not going to be happy because in fact why do I get a warning there? Yeah, it's not going to be happy about that either. Yeah, C++20, yeah, we know. Because this is concepts all the way, so my editor uses the default flags for G++, and I really need to compile this with dash std, etc. So let's go to concepts. Let's try to do that properly. Okay. So G++ simple, and C is C++20, otherwise I'll get trouble. All right, so that compiles and runs, no problem. Okay, let's increase font size a bit. Okay, let's go back now to the code and let's see what happened when I comment this guy out. Well, this should not be I, but some. Okay, so this is without concepts. Let's compile. Okay. Okay, so this is actually still quite reasonable. Error converting from const into non. Yeah, okay, this is still quite reasonable, in fact. It's not such a good example. I thought it would be a bit more impressive. But of course, it boils down to the fact that we can't convert a string to an integer. I had hoped for more sophisticated error messages. Let me comment this guy out and comment this guy in. And then you see you get a longer error message, but it is a little more intelligent because it says, well, okay, there are candidates, but there's something wrong because this cannot be converted to, etc., etc. So in this case, okay, you can argue which error message is simpler. So I would actually, in this case, call this one simpler, so the original one. But I think you can imagine that when things get a bit more sophisticated, that this is a pretty straightforward error message and that it will actually tell you what is going on. So basically in this case, of course, we want some type as an argument that can be converted to a string, and that's of course not the case for our integer. So that's why this goes wrong. Okay. All right, so that's a little bit about concepts and why we would want to have them. But this is really, really standard 2022. So that's pretty much on the edge of what compilers do. You need a recent compiler to get it working. Okay, I need to talk a little bit about IO streams because we didn't do that. And then we'll talk a little bit about strings and regular expressions. Okay, so we need to go to IO streams. All right, so we've already used streams, easy, because that was just std c out, std c error, std c in. But there is a bit more to it, and basically we can actually create our own output streams as well. So basically an output stream, it converts object to a sequence of characters. We already know. It does type conversion automatically with the send-to operator. Similarly for input streams, we're going to read from input streams. We get automatic conversion to the appropriate type and so on. So that's all old hat. We know how this works. Okay, so strings, integers, strings, double, another string, etc., etc. Quite easy. Okay. Yeah, okay, that's correct. All right. So we know how that works. That's easy. The standard streams we know, std out, cerr, and we have the put to or the send to operator. Then cross-platform end of line. We know that input stream is std in, and the get from operator. We are very familiar with that. It skips initial white space when reading, and that's basically a space, a tab, a new line, carriage return, form feed, and so on. Default separator is white space, so that's easy. If you want to read an entire line, including the end of line, you can just use the getLine function. Okay, so the stream state, the result of the put to operator, the get from operator is essentially a reference to an input stream. So basically, a reference to an input stream evaluates to true if it's ready for reading. So in other words, if it can read again. So for instance here, while std in get from data succeeds, it is going to continue. So each time the read could be done, the while loop is executed. As soon as in the input stream there is something that cannot be converted to, in this case, a double precision number, then it stops. Then it evaluates to false, and the while loop will end. That's basically the idea. You can also explicitly check the end of a file, and that's just with the EOF, end of file method. Okay. One thing I also didn't mention is that you can actually format floating point values in a more interesting way. So basically, what you typically have is, I don't know what the default is. Yeah, default float, obviously, but not quite. Have to kind of try and remember what it is. But anyway, so you can switch to scientific format, to fixed format if you like, and basically you can also set the precision. You can get it and you can set it. So that is convenient to make sure that you get some reasonably formatted output. For instance, in this case, we compute pi, and then we just use the default, nothing special. Then we do it in scientific format, and we set it to default float again, but in this case with a certain precision. Okay, so we would get this by default. Now in scientific notation, we would get the same number, well, we get one digit more, but with E0 appended. If we specify that we want 4 digits, then indeed that's what we get. Okay, so typically what you do is you get the precision by a call to C precision, C out precision. You store that, you change the precision, you do your output, and you set it back to the value you previously had. That is good practice. You can also set the width and the fill. So basically, this would make sure that you have a width for the next output of 5 characters. And you can also set a fill character. For instance, if you have a width of 10 for integer and you print 5, you would get 0 lines followed by a 5 if you set the fill value to 0. Here's an example. So we have 123. If we just print that, of course, we get, surprise, surprise, 123. Now we assign the original width to a variable. We set the width to 5, and we also store the original fill, and we set the fill to 0. So then we will get 0, 0, 1, 2, 3. And then we restore the original width and the original fill later on, so that we don't disturb further output. Okay, because of course Cout will remember. Unless you change the fill again, it will keep on filling with zeros, and that's probably not what you want. Okay, so that's for standard out, standard error, standard input. And in fact, same thing holds for arbitrary streams, because you can create an input stream on a file. So IF stream is input file stream, and F stream is a file stream. And in order to use those, you need to include the F stream header. And you can simply create a new input file stream by specifying the file you want to read from. And that's automatically opened for read, of course. And then as long as, if that is not, if that contains something, so if not IFS, if this evaluates to false, the file was not open. So you do something in order to whatever. And then, of course, you can start reading from that file, and you can do that in the exact same way as you were reading from standard input. So that is really very easy, very convenient. Everything you know about CIN also applies to input file streams. Very easy. And of course, if you open a file, you should also close it. There is no such thing as context managers in C++. So basically, if you open a file, you're supposed to close it. Okay. An output file stream, OF stream. So file stream, but now for output. Similar thing. You just create it based on the data type. It's open for writing. Test whether you manage to open it by checking whether it doesn't evaluate to false. And then you can just write to it, just like you did with std cout or std error. And at the end of the day, don't forget to close it again. Easy. Something that's also very convenient is string streams. And that's in the header s_stream. And basically that allows you to apply the send to and get from operators to a string stream. So you start out with an ordinary string, and you create a string stream out of it. So here we create a string stream out of line, which we got from standard input. And then we can simply use the get from operator on that string stream to read values from it. And that can be very convenient. So in this case, I'm storing data into a vector. And here I'm doing this repeatedly. I'm just going to find a separator and read time after time the value. So basically, I'm supposing here that I have a line of data which is separated by, for instance, commas or semicolons or something like that. So basically, between each double value in textual representation, there is some character which is a separator. That's the idea. Okay. Is this more or less clear? Okay. So that was about streams. That means that we covered everything except for strings and for regular expressions, which we'll start now. But maybe first, are there any questions? Because I know that some people are really not interested in strings and regular expressions. They might want to stop here. But are there any questions at this point? If you have any questions, this is a good moment to ask them. Okay, no questions. Before we continue, I realized that during the break I forgot to do something, which is okay, come on. Okay, that's better. All right. If I don't, the Secretary's office is going to be cross with me, and that is a little annoying for all parties involved, especially for me. So, okay, come on, I want my desktop. Okay, and now that is 0301. Right. Administration done. Okay, let's turn to strings and regular expressions. All right, so working with strings and regular expressions in C++ is kind of okayish. It's a little bit more involved than what you're perhaps used to in Python. So typically, I would say if I would have to do text processing, I would do this in Python rather than in C++, unless, of course, I really need the performance. But for Python is more convenient for this type of thing than C++. So I'd only do it if Python is not fast enough. Okay, and then of course, again, you also have to keep in mind that one of the limiting things here is how fast can you read a file. And that is typically slow. So that's why C++ might perhaps not give you the performance boost you hope for. Okay, let's talk a little bit about strings first. So string is a data type in C++, and it's essentially a sequence of characters. So we can create a string by simply specifying its value. That's quite easy. And the append operator has been defined on it. So the append operator is simply the addition plus sign. So basically, if I add space world to string str, then I get hello space world. Okay. What you can also do is take substring, and probably I have the output. So in this case, we go from character 6, and we want 5 characters. So personally, I kind of like this approach in the sense that what you typically have for substring, for instance, if you think of substring in Python, you're going to do that by slicing. And then you always have to think, well, okay, I actually want 5 characters, so I have to add 5 to this. Is it 5 or is it 6? No, it's 5, or is it whatever? So basically, personally, I like this. Just the position where you want to start and the number of characters you want. Anyway, you can also find something in a string. And in this case, if you, this would be 5, of course. So basically, I'm going to replace that by an uppercase character, and I'm also, in a different way, going to replace the first character with a length of 1 by the string age. So this is actually substring substitution, again, begin position, length of what you want to replace, and what you want to replace it by. So the W is replaced by capital W. So we have the std to upper method, which will convert a string to uppercase. And I'm assigning that to string at position pos, which I found using the find method. Okay. Then I can also search to a string repeatedly by having a second argument to find, which is the starting position. So here in this particular case, I would just iterate over all the occurrences of O in this string, and of course there are two. There is one in hello and there is one in world. And when find doesn't find anything, it will actually return string and pos, so no position. And that means find didn't find anything. So for instance, in Python, this would be -1, or it would be it would throw an exception depending on which string find function which you use, because you have on the one hand find, on the other hand search if memory serves, and one throws an exception, the other returns -1 if nothing is found. Here in C++, it's just a special value which is defined in std string, and that's std and pos. Okay, so if you would do that, then of course you would get 4, because string indexing is 0 based. So 0, 1, 2, 3, 4, 5 for the space, 6 and 7 for the second O. Okay, you can also insert a string at a certain position. So if I insert at position 6, so that would be 0, 1, 2, 3, 4, 5, 6. So in front of world, we will insert beautiful space, and then we get this. So very convenient. I would say resembles Python quite a lot. Names of the functions are not always the same. Semantics is sometimes a little different, but nevertheless, things are pretty straightforward. Okay, so I already mentioned that we also have C-style strings, and in my opinion, there's only one reason to use them, and that's basically in argv, because we don't have a choice. That's just how C++ works. The arguments to main are an integer and an array of pointers to character arrays. Because now you know what char star means. That is an array of pointers. Well, that's a pointer. So basically, if that's an array, it's an array of pointers. Okay, so C-style string is an array of characters, and the last element by convention is always this special character, the null character. So functions for dealing with C-style strings are defined in string.h. It can be useful if you need to call C functions, then that might be useful. But on the other hand, you can also very easily convert a C++ string to a C-style string by just using string .c string. And getting a C-style string into a string converted is just using the std string constructor, so that's trivial. Okay, so that's a little bit about strings. So it's a versatile data type, and as you can see, there is another difference with Python. In Python, strings are immutable. In C++, they're definitely not immutable, because, for instance, the insert method has actually changed string. I can assign a new character to a character in a string at a certain position. So all of this works in C++. Of course, in Python, it will definitely not work, because basically that is an immutable. Okay. I've already mentioned it. Regular expressions. Okay. What is a regular expression and why would you need it? Well, at an abstract level, a regular expression is in fact a description of a language. And what is a language? A language is just a set of strings. So it defines a set of strings, and that is actually quite powerful. So such language or this set of strings can be finite or infinite. Of course, the set of all strings is definitely infinite. I mean, I can always, even if I have a single character like A, I can create infinitely many strings, because the empty string would be a string. The string with character A would be a string. The string with character AA would be a string. The string with characters AAA would be a string. So obviously the set of strings is infinite, but it's countable. So basically it has as many elements as there are natural numbers or integers. Okay, so there is actually a hierarchy of languages, so of sets of strings. And at the sort of bottom, you have the regular languages. They're the most simple ones. Then you have context-free languages, context-sensitive languages, and recursive enumerable languages. So all languages are recursively enumerable, that's for sure. Some are context-sensitive, some are context-free, and some are regular. So to give you an example, C++ is a context-free language. Basically, that means that the set of all legal, syntactically correct C++ programs, all the C++ code you can write, is in fact a context-free language. But we're not dealing with that because that's a bit more involved than regular expressions. So, okay. I obviously copy-pasted this from a Python presentation, and so there's still Python regular expressions here. So, but make that C++. They are also a little bit more expressive than actual mathematical regular expressions, regular languages. Okay. What's the expressive power? So basically, what can you describe by a regular expression? Don't ever try to do HTML or XML with regular expressions. Don't do that. It's really a very bad idea because those are context-free languages. And a context-free language is definitely much more complex than a regular language. So similarly, don't try to use regular expressions in order to parse C++ or Python programs, because those two are regular languages and context-free languages, and that's not going to work. Even if you think you can, probably you shouldn't. Okay. Can you, for instance, write a regular expression that describes all regular expressions? And the answer is no, because the language in which you write regular expressions is in fact context-free as well. So, can you parse English using regular expressions? No, because actually English is even more complicated than context-free. It's actually context-sensitive up to a point. So that doesn't work. Let's give some examples of what would work. For instance, if I want to, you're familiar with the DNA sequence. So basically, that's a sequence of nucleotides. You have 4 nucleotides for DNA, A, C, G, and T. And so I can describe the set of all strings that describe DNA, that are regular DNA, by specifying square brackets, ACGT plus. So this is my regular expression. There are two parts here. There is the thing between brackets, and this means the string can contain characters that are A, C, G, and T. So basically this is a set of 4 characters, and if I write ACGT, that means that a string must have a character that is either A, either C, either G, either T. Okay. Then we have the plus, and that's a repetition operator. And the plus means whatever is in front of it, 1 or more times. Okay, so that would give me the following set of strings. Let's pull up a line break. Oh, come on. All right. Okay, so that would give me the following language. So the empty string is not among them. So we would have A, we would have C, we would have G, we would have T. So strings with 1 character. Then all the strings with 2 characters, AA, AC, AG, AT, etc. So all combinations of 2 characters, and then all combinations of 3 characters, all combinations of 4 characters, all combinations of etc. etc. So as you can see, this is going to be an infinite set. That's pretty obvious. Okay. Another example, DNA. I want to describe DNA that contains the substring AAT. So basically that means that either AAT can occur at the start of my string, it can occur anywhere in the string, or it can be at the end of the string. But at least there must be one occurrence of AAT literal. So if you just put parts of an expression one after the other, like here, we have actually 3 parts to our expression. We have square brackets star, that's the first part of our expression, then AAT, that's the second part of our expression, and square brackets star, that's the third part. So if we put things one after the other, that's actually just means that expression 1 is followed by expression 2. So this is one expression. In fact, A by itself, you can also consider an expression, or you can say, well, okay, this is just a literal AAT, and that's the third expression. So the concatenation operator for expressions is implicit. You don't write it, but you should think it's there. And then we have the star operator, which is very similar to the plus operator, only it means 0 or more times. So that means that the shortest string I have in this language, so the shortest string which is described by this regular expression here, is just a string AAT. And then strings of length 4, for instance, A, AAT, C, AAT, G, AAT, etc. Or AAT followed by a character, AATA, AATC, etc. Or something in front, something after it, CCTGA, AAT, AGTTT, whatever. Okay, so alternatives we can also express. So if my string should contain AAT or TAT, I can express it like this. So this is an alternative. Either I've got AAT or I've got TAT. The operator is the pipe operator. So that's an OR, essentially. And it's either or. Okay. So another example. This could be a regular expression for Belgian landline numbers. So Belgian landline numbers start with an area code. An area code always starts with a 0. Then it is followed by any digit which is non-zero, so basically 1 to 9. So this is a shorthand for square bracket 1, 2, 3, 4, 5, 6, 7, 8, 9. So this just means, the dash here means any character between 1 and 9. Okay. Then, so that's the first 2 digits of our area code. Starts with 0, then 109. And then optionally any digit. So \d means any digit. So that is in fact the same as 0-9. I could also write that, but yeah, okay, that's 2 characters more. No, that's actually 3 characters more, so why would I do that? And it's followed by a question mark. This question mark is again a repetition operator, but it means 0 or 1 time. So up to the slash, forget about the slash for a second, we have our phone number must start with a 0, then it must have at least 1 non-zero digit, and then it can be followed by any digit, optionally. So if we just look at this part of the expression, 0 or 1 would be valid. 011 would be valid. 090 would be valid. 04 would be valid. Okay, so then we continue. We have the slash, that's a literal slash, so that's easy. And then we again have 1 to 9 because the actual number doesn't start with 0. And we again have any digit, and now again a repetition operator. 5 to 6 times. So basically, curly bracket m to n means at least m, maximum n occurrences. And in this case, we have either 5 or 6 digits. All right, so that means that 011, 26, 81, 11 would be okay, because 0, 1, 1 slash 20, so 2, then 5, 6, 8, 1, 1, 1 would be 5 repetitions of, yes, 5 repetitions of a digit. So that would fit. Okay, for those of you who are familiar with Belgian landlines, is this in fact okay? In the sense that there are 2 directions in which you can look at this. So does this regular expression describe all Belgian landline numbers? Forget about the 0800 and things like that. So we're only talking about the regular ones here. So does it describe every Belgian landline number? Yeah, the answer would be yes to that. If I have a valid phone number, then it will be described by this regular expression, no problem. But is the inverse also correct? So let's assume that all valid numbers are in fact in use. So no, if a number is not in use, it doesn't matter. But would this allow for phone numbers that are definitely not valid? And the answer again is yes. Because what could I do? I could have a 3-digit area code followed by a 7-digit phone number. And that never happens. That would be that would be incorrect. And that is allowed by my regular expression. So of course I can fix that, but I wanted to point it out because this is a very easy mistake to make with regular expressions. You really have to make sure that your regular expression describes all the strings you want to describe, but also that it does not describe strings you don't want to be part of your language. So that's kind of important. Some other things, you can have all the strings, including the empty string, by dot star. So dot means any character, and star means 0 or more. So this is the set of all strings you can possibly form. So for instance, we could also try our hand at an email address. So basically, an email address consists of any character which is A to Z, lowercase a to lowercase z, any digit, and an underscore. Okay, that's our set W, and we can have one or more of those. And then optionally, we can have a dot, and now we should precede this with a backslash, because dot in fact means any character. So if we want a literal dot, we need to insert a backslash, and then any character again, and that's optional. So this here is a grouping operator, is our grouping brackets. So the question mark column are actually part of this opening bracket. So this is one opening bracket, and that's corresponding closing bracket. So this is a grouping bracket. And then we have a literal @ sign, and we again have a word, followed optionally by one or more dot words. So basically, again, an example of a regular expression and some more syntax which you can use. Don't do this. Never ever validate email addresses this way, because actually the specification for what is a valid email address is, if memory serves, a document of something like 700 pages. So this is not really describing it. Okay. So these brackets are really the brackets which you use in mathematics. So that's a little inconvenient that you have to remember to add this question mark column thing, but that's a performance thing. You can leave it out, but then you get different semantics and things would be a lot slower. Okay, so some more things. Some characters you have to escape, \T for a tab, \N for a new line, \R for a character return, \\, if you want a literal backslash, all the brackets, all the operators, and of course the dot. All other characters are literal characters. So you have character classes. A character by itself is just the character. Between square brackets gives you the set, in this case of x, y, and z. You can also express that by a range of characters, and again, you get all the characters between x and z. You can negate that, so basically caret x, y, z in square brackets means any character except for x, y, and z. So you have negation here. So this backslash here means set difference. \W we already encountered, so that's all characters, all letters and digits and underscore. \W is the complement of that. \D is all digits. \D is everything but a digit. \S is white space. So that's basically space, tab, form feed, carriage return, new line, and vertical tab. You never ever see vertical tab and, well, okay, form feed was for printers back in the days. Probably you never ever see them. And of course, \capital S is again anything but white space. And then, sorry, a dot is any character except for a new line. A new line is not captured by a dot. Okay, so operators, we have the concatenation, which is implicit. If you just put two expressions after another, it means concatenation. We have choice, either expression 1 or expression 2. And then we have repetition. So we can say that an expression occurs exactly n times by putting n between curly brackets. Or that it occurs at least m times and maximum n times, anything in between. Or that it occurs 0 or more times, but at most n. Or that it occurs at least m times, but as many as you like, as long as it's more than m. And then, of course, there are some special cases. Question mark means 0 or 1, so that would in fact be the same as expression 0, 1, or would be the same as expression 1 between curly brackets. And then we have the star operator, that's 0 or more, so that would be equivalent to curly bracket 0, curly bracket. Or 1 or more, that's the plus operator, that would be equivalent to curly bracket 1, close curly bracket. Okay, why do we have these special cases? Basically because the last three were there first, and then later on they introduced the bracket notation. Okay, what you have is longest match semantics. So basically you keep on matching as long as you can. That's quite important, and that's actually what is happening here. So I'm doing something that I shouldn't do, and that is parsing a fragment of XML. Okay, so what I want to do is to match the starting tag here. So that's everything from the less than up to this larger than. So that's the start of my HTML or XML tag. Okay, so I could do that by saying, well, okay, my regular expression starts with less than, so that's this guy, okay, and then any character up to a larger than, okay. Now the question is, what will that match? Well, we have longest match semantics, so we start matching, we see, okay, larger than, that's fine, less than, that's fine. Then any character I want, okay, V, A, R, space, name, etc., etc., larger than 1, 5, blah, 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 okay, and now larger than. So it will capture everything because we have longest match semantics. That's of course a design choice, and it's just a design choice which the designers of regular expressions decided to use. But you must be aware of it. So what you can do is use a non-greedy operator. So for every repetition operator, you have a non-greedy version, and that's just by append a question mark to it. So in this particular case, it will non-greedily match one or more occurrences of any character. So if we do that now, we have less than, okay, VAR space NAME equals quote X quote, stop, larger than. And it will match exactly this. So for each operator, you can just append a question mark, and then you get a non-greedy version of that. And that applies to the star, that applies to the plus, that applies to the question mark itself, and to the curly bracket stuff. Okay. So why not parse regular expressions with XML with regular expressions? Well, basically, this seems to be fine because we want to parse a variable name, well, the begin tag, so that's fine. But what happens now? Because in my string, of course, there can be a larger than, and my regular expression has absolutely no idea that this is part of a string rather than a closing tag. And there is also no reasonable way of doing this with regular expressions. The reason is, of course, that XML, just like Python, just like C++, just like name your favorite, is a context-free language. And regular expressions are strictly less powerful than grammars for context-free languages. So don't do that. So basically, okay, again, Python's libraries. I would actually have to look for equivalent libraries for C++. No doubt they exist, but I'd have to check for them. Normally, what you do if you have a context-free language is you write your own parser, and there are tools for that, like for instance Antler, who do that for C++. It would generate a C++ parser based on grammar specification. There are alternatives to that. Antler is one. There was one which I used for a project, which was not Antler. I don't remember. It's too long ago. Okay, now one of the things which you may have noticed is that regular expressions contain backslashes all over the place. But you also know that in C++ strings, backslashes should be escaped. If you want a literal backslash, you have to escape it. So if this is my regular expression, the string representation of that would be pretty horrible, because I would have to remember to precede each backslash in my regular expression with an escaping backslash to make it a valid C++ string. So that's, of course, extremely annoying. That's why, just like in Python, you have in C++ the notion of a raw string. So a raw string is enclosed by R double quotes and then a left round bracket. And it's ended by a round bracket double quotes. So in Python, you would write R quote and you would end with a quote. So here it's R double quote, round bracket, double quote. And in such a raw string, the backslash has no special meaning, and I can write my regular expression without getting hopping mad within 5 characters typed. Okay, so how can we use regular expressions? The regular expression library is in the STL, so we just include regex. And we define our regular expression by some raw string, and then we can do a search. So we do a regex search on string, and we use expression. This is also annoyingly different from Python, because in Python, the search function would in fact take the expression as the first argument and the string as the second argument. So here it's vice versa. So for those who come from Python, yeah, pay attention. Okay, so getting the string which was matched, because note, here we do something slightly different. We have the round brackets. Wait, we don't. No. So basically, if we want to get the part which was matched, just a second, what am I doing here? Matches. Yeah, okay. So I pass I create an smatch object, and those are the matches in my string. And there is a typo, which was what got me confused. There should not be an R here, it's just matches. And basically, and then you can check what was matched. Match 0 is always the entire string which was matched. So that's similar. If you have a match object in Python, you can use group 0, and that will return the entire string that was matched. So you can use regular expressions in order to extract parts of a string. So remember, for grouping, we had the grouping parentheses. So round bracket or parentheses, question mark, colon, and round bracket. You also have capturing brackets, and that's just easier. It's just a round bracket. So now in this case, note that we have added round brackets here and there. So everything that is matched in between those round red brackets, so the new ones, that is stored in matches. And similar here, that's the second part which we match. And I think there is a round bracket missing, because this is a raw string, and there should actually be a matching round bracket here. So that's another typo. Again, I have my matches thing, I pass it, and now I can use matches 1 and matches 2. So matches 1 will be what is matched here, matches 2 will be what is matched here. So if we apply this to an email address, then matches 1 will contain everything before the @ sign, matches 2 will contain everything after the @ sign, so the domain name typically. So that's what's happening here. So you can use capturing brackets to group, but of course, if you do capturing, there is lots of machinery going on. If you just want to group for performance, it's better to use grouping brackets rather than capturing brackets. Okay, you can also use this in order to do replacements in strings. So you also have a format string for replacement. And then $1 is the first capture, $2 is the second capture, and so on. And $ampersand is going to be the complete match. So basically, here in this case, we have a string, and that string is representing a list of things. And what we actually want is that list of things, but each item in the list, so 1.5, should be enclosed by single quotes. 2.3 should be enclosed by single quotes, and alpha should be enclosed by single quotes. So what we want is single quote 1.5 single quote, comma, space, single quote 2.3 single quote, comma, space, single quote, alpha, single quote. Okay, can we do that? Yes, we can do a regex replace. We do that on string with the expression. The expression is we capture, that's these round brackets here, the second round bracket. We capture any character which is not a comma, and I think there is a space here which shouldn't be there. So any character that is a comma, and we want one or more of them. That's our expression. So we will capture all the parts of our of all the items in our list, and we are going to replace each match by the value which was matched. So that's $1, enclosed by single quotes. And so what we get is indeed 1.5 in single quotes, 2.3 in single quotes, alpha in single quotes. That's the idea. So that's your regex replace. So we can use regular expressions to check whether a string matches a regular expression, so whether it's part of the language, and we can also use it to replace things. We can also use it to get parts out of a string and so on. If you want to iterate over matches, that is, again, not so very hard. So this would be sort of tokenization of your string. The thing is a little involved, so let's perhaps skip over it. But the idea is you have an iterator, a regular expression iterator, and this is basically constructed by going from the beginning of the line to the end of the line on an expression, and then you get a token, and basically when you don't get a token anymore, you stop, and the token is the actual match in the regular expression. So it's a little involved, but basically that would capture, in this case, all the words in a sentence. Okay, it's actually bidirectional. The stop condition token you have to use here. So you can't just use the end of the string or something like that. You really have to use a token. Okay, so basically the match was capturing. Here are the round brackets, and of course that's why we can do we can take the first match, which is basically whatever was captured. In fact, in this case, we would not even have to bother, because we have a very simple regular expression which just takes all the words. So essentially we could even leave out capturing brackets, and we could just use the 0 component of the token, because that matches the entire, that has the entire string in it. So that would in this case be equivalent. Okay, so regular expressions are quite powerful. Don't use them if you don't need them, because they're of course slower than regular string search. If you just search for a substring, don't use regular expressions. It will be a lot slower than just using the find method on strings. So use it carefully. So you can also work on streams. So basically, it's a bit more versatile. Match works on strings, so you get better performance. So basically, you can do multiple things. You can have modifiers, so you can say that that a match is case insensitive by having an additional argument in the constructor, regex iCase, so case independent. Okay, so I didn't talk about string implementation. That is in the chapter of the book. But I think I added some stuff on regular expressions. I don't quite remember. Okay, so are there any questions about strings or regular expressions? Are there any questions about C++ in general? Okay, then thanks for attending, and I hope it was useful for you. So enjoy the rest of the day, and maybe I'll see you at another training.